Log on, tune in, find out. Another good idea from Cambridge.
Cédric Bonnafé, who will continue his lectures on Kazhdan-Lusztig theory with unequal parameters.
Thank you. Well, so I have just recalled here the few notations that will follow us all along this series of lectures. So I recall that we are working with a Coxeter system. The equal algebra is defined using a quadratic relation involving a function phi, which is constant on conjugacy classes of simple reflections. But this function can be non-constant. That's one of the points in these lectures. And we have almost proved the Kazhdan-Lusztig theorem, namely that there exists an element CW satisfying the following two conditions. It is invariant under some involution that I have introduced yesterday, and it is congruent to TW up to monomials involving only negative powers. Well, I recall also some properties of these Kazhdan-Lusztig elements that follow from the sketch of the proof I have given yesterday. And for this, I will assume from now on that for all S in S, phi of S is greater than 0. So this is an assumption. This is an assumption. In fact, we can reduce to this case. It's possible to reduce to this case, and in this case, the behavior of the Kazhdan-Lusztig polynomials and of the constant structure in the Kazhdan-Lusztig basis is much better. And if we write the Kazhdan-Lusztig element in the standard basis, then we have the following properties: that the diagonal coefficients are equal to 1, and the coefficient is non-zero if and only if x is less than y for the Breuer order. So in other words, the transition matrix from the Kazhdan-Lusztig elements to the standard basis is unitriangular, and the coefficient above the diagonal all involve only monomials with negative powers. And in particular, this tells you that the Kazhdan-Lusztig elements form a basis, and we can consider the multiplication by elements CS. So if Sy is greater than y is less than y, the multiplication is easy. The Cy is just an eigenvector. And if Sy is greater than y, Cy is Csy plus a sum involving only elements x, such that x is less than x, and the coefficients here are in general very difficult to compute. But at least what can be said is that in this sum only elements such that Sx is less than x are involved. That's the important thing. Well, and of course, so that's what we have almost seen in the example of B2 that I have done yesterday. Of course, we can do the same thing by using the multiplication on the right, and we obtain exactly the same kind of statement. So if ys is less than y, then cy cs is the exponential of phi of s plus the exponential of minus phi of s cy. And if ys is greater than y, then cycs is equal to cys plus a sum involving only element satisfying this property. Okay. Well, so that's almost what we have seen quite quickly yesterday. And the first consequence of this, of the property of this multiplication that can be proved by induction, is the following result. Is that if you consider the following R module, the module generated by the CYs satisfying the following property, if you multiply them on the left by a simple reflection S, the simple reflection S, then this element is smaller than Y. So this is equal to the set of H of elements in the equal algebra such that H times CS is equal to a multiple of H, the multiple being given by this. And in particular, once you prove this, this tells you that this guy is a left ideal. The fact that it is a left ideal follows from this equality. And let's prove this this fact. So consider let E be the set of Y in W such that Ys is less than Y. Then W is the disjoint union of E and E times S. And what? And if you consider mu the map from H to H that sends H to the multiplication of H by CS minus this guy, this scalar, and if you express the matrix of mu in the Kazhdan-Lusztig basis, but this in a block form, so here put the elements of E, ES, and here ES. So if you multiply a CY for Y in E, then the multiplication, then the map mu sends CY to 0. So here you get zeros. And if you multiply a CY such that which is in this set, the elements are satisfy YS is greater than S. So if you look at what you obtain, it's given here. You obtain only elements which live in E. So you obtain something here, and you have diagonal coefficient. Let's call this guy QS. So you obtain minus QS minus QS. Okay. So once it is written in this form, it's clear that the kernel of mu is equal to the sum for Y in E of the RCY. It's really easy linear algebra. Well, so that's the first consequence of this of the rules about the multiplication on the left or on the right by an element CS. And I recall that CS is TS plus the exponential of minus phi of S. So in other words, the CS generate also the algebra H as well as the TS do. Well, let me add a last property of the Kazhdan-Lusztig cell, namely that it is possible, the Kazhdan-Lusztig polynomials, namely that it is possible to go from multiplication on the left to multiplication on the right by using an anti-involution. So let's start with the map going from H to H. In that sense, the exponential of gamma to itself. So it is, the map is R linear, and it sends an element TW to TW inverse. So this one, by opposition with the involution bar, the involution bar is semi-linear, but it is an automorphism. This one is linear, but it is an anti-automorphism of algebra. And it is involutive. And because of its construction, it's very easy to check that it commutes with the other involution. And from this, you deduce immediately that if you apply the star involution to a Kazhdan-Lusztig element, you obtain the Kazhdan-Lusztig element associated to the inverse. So for instance, in these rules, you can immediately see that there is a link between the left constant for the multiplication and the right ones. Okay, so you can switch from the between the left and the right easily using this involutive automorphism, anti-automorphism. Well, so now using the Kazhdan-Lusztig basis, we can make the construction. I did it yesterday quite quickly. We can redefine what is the Kazhdan-Lusztig preorders using the Kazhdan-Lusztig basis. So we say that X is less than is in elementary relation with Y on the left if there exists H in H such that Cx occurs with a non-zero coefficient in HCy, in the multiplication of Cy by an element. And this defines a preorder like this, and an equivalence relation associated to the preorder, as we did yesterday. And of course, one can define the right preorder and the right equivalence relation, and the left-right preorder and the left-right equivalence relation. And using the anti-automorphism, the left preorder can be computed in terms of the right preorder just by taking the inverse. And of course, the same holds for the equivalence relation. Well, so why should we be interested in computing these preorders or just the equivalence relation? I will give a list of possible application of of the Kazhdan-Lusztig theory to geometry or to the representation theory. So first of all, I want to talk about the equal parameter case. So in the equal parameter case, I mean that gamma is equal to z and phi of s is equal to 1 for all s. So you recognize a one parameter equal algebra. So in this case, there is a link with a geometry of Schubert varieties. And roughly speaking, it goes through an interpretation of this derived category, plus action of the Frobenius, if you are over a finite field, and the Grothendieck group of this guy is isomorphic to the equal algebra. This is quite sketchy. I just want to say that the simple elements here through this isomorphism correspond to the elements in the Kazhdan-Lusztig basis. This relation corresponds to the Poincaré duality, and this one is just a condition on the support of a simple modules. It tells you that it is in the closure of a Brugha cell, of a Schubert variety. Yes? This I don't know. Maybe. Jordi, what do you think? Not necessarily. Okay. But yeah. Okay. And for instance, from this geometric interpretation, you can get that the coefficient of this, the coefficient of Cy in the standard basis are in fact non-negative. So there is no negative signs in this, but you can get more than this. Just the sum for gamma in gamma of n exponential of gamma. Yes, non-negative coefficient. Yes, that's all. Well, so there is also a link with the theory of primitive ideals of enveloping algebras. There is also a link with the geometry of the unipotent variety, namely the special unipotent class of G are in bijection with the two-sided cells of W. Well, here I assume that W is the Weil group of the corresponding algebraic group. And there is also a bijection between the unipotent classes and the two-sided cells of the affine Weil group. Let's say W tilde, where W is the Weil group of G. So that's so you see that in the equal parameter case you have many links with geometric objects. But there are also applications for the unequal parameter case, so for the general case. What? What do you mean? Sorry?
Like it should be constructible with respect to the g-orbit.
You mean the what I have written with the g? I didn't want to write something precise. Okay. Okay, and in general, so not only in the equal parameter case, here the applications are much more algebraic. So first, this leads to constructions of small H modules. By small, I mean that they are close to be irreducible once you extend them to the field of fraction. And in fact, well, let K be the field of fraction of R. So R, this is a group algebra of gamma which is totally ordered, and because it is totally ordered, this group algebra is a domain, so you can talk about the field of fraction. And in this case, KH is split semisimple. And you can consider if C is the left tail, well, it's interesting to understand the structure of the extension to K of the module which is associated to the left cell. I have defined this yesterday. In the case of finite Val groups, finite coccurator groups, these representations are in general very small. For instance, in the case of type A, you get all the irreducible representations like this. In a type B, for certain choice of parameters, you can also get irreducible representations. But even if you don't get irreducible representation, type B or B, you get only multiplicity-free representation, and there are not so many irreducible components. So that's close to be irreducible. And even if this guy is not irreducible, in fact, they are important in the representation theory. Of finite reductive groups. Well, of, let's say, G of K, where K is finite, or K is a periodic field. In the case where K is finite, this is a finite Val group which is involved. In the case of a periodic field, one has to work with the affine Val group. That's all. And last algebraic, last representation theory application of Kazhdan-Lusztig theory is what happens in type Bn. In type Bn, we can give an interpretation. Well, the modules VC should be an interpretation, I will be a little bit more precise, of Haricki's theorem. About decomposition number at roots of unity using the action on the Fock space. I don't want to be more precise than this, but you have already seen things like this in Meinhof's talk. Sure. Well, so this is a list of motivation for studying Kazhdan-Lusztig theory. So you see that in the equal parameter case, there are geometric applications. Geometric applications which have also application to representation theory, as for instance it can be seen in David Vaughan's lectures, the geometry of the Schubert varieties related to the representation of real reductive groups. In the general case, there are applications which are, in some sense, only algebraic, and a geometric interpretation is missing for the moment, except that we expect that Lusztig will give one. I don't know when. Okay. Well, unfortunately, I will not talk about any of this subject. I just want, in this introductional series, in this instructional workshop, I just want to talk about the algebraic, combinatoric and algebraic properties of the Kazhdan-Lusztig cells, Kazhdan-Lusztig basis, that are necessary in order to start to understand the other subject. You can see this as an introduction to study whatever you want among all these subjects. Well, if one of the first problems in this theory is to compute the left cells, the two-sided cells, the left or the two-sided preorder. So that's one of the main themes of this lecture, to compute the relations following relations. So yesterday I gave an example in B2 where I have computed the left cells according to the different possible choices of the parameter. But there are many general properties of the left cells. And the first one is given by the following proposition. So if x is less than y, well, left less than y, then the right descent set of y is contained in the right descent set of x, where the right descent set is equal to the set of S in S, such that ys is less than y. And in particular, if x is equivalent left to y, then they have the same right descent set. Well, so this tells you that the left cells are non-trivial, namely there is, as I have said, you can define a preorder using any basis. If you use a standard basis, you get a stupid preorder because you will get only one cell. By using the Kazhdan-Lusztig basis, this result tells you that you will get, a non-trivial partition of the Weil group. Okay. So let's prove this result. So if x is less than y on the left, it means well, we can assume. So we can assume that x is just directly related to y by left multiplication, just by transitivity. So in other words, so x belongs to the left ideal generated by cy. Well, cx belongs to the left ideal. But if S belongs to the right descent set of y, this means that ys is less than y, then the left ideal generated by cy.
I thought the relation said that Cx had to appear if you express, how do I say it? That if you express the Hecke algebra times Cy.
Okay, you're right. Okay. Well, Cx divides. Cx occurs with a non-zero coefficient in HCy. Okay, thank you. For some h in h. But if S is in the right descent set of y, then the sum for Ws less than W of RCW is a left ideal. That's what we have proved here. And Cy is an element in this particular left ideal. So it tells you that HCy also is an element in this ideal. So since Cx appears with a non-zero coefficient in HCy, this implies that XS is less than X, which is equivalent to say that S is in the right descent set of X. So if S is in the right descent set of Y, it must be also in the right descent set of X, because this guy up there is a left ideal, but just the same thing. So that's the first property of the Kazhdan-Lusztig cells. There are other ones which are related to parabolic subgroups. So if I is a subset of S, we denote by Wi the standard parabolic subgroup generated by I. And it's well known that Wi is a Coxeter system. And we can also define Hi to be the subalgebra of H, which is the sum for W in Wi of the RTW. And associated to parabolic subgroups, there is a distinguished set of representatives of the cosets, which I will denote by Xi. This is a set of X in W, such that Xs is greater than X for all S in I. And this is also well known to be equal to the set of X in W, such that X has minimal length in its coset, in its Wi coset. And this coset is in bijection. This subset is in bijection with the coset modulo Wi by sending x to xwi. This result tells you just that in each such coset there is only one element of minimal length and that it is characterized by this. In particular, you get a bijection between the product of xi and wi with w, and it sends a pair xw just to the product. So you can define two projections, one on xi, one on wi, that I denote by pi I and psi I, and it sends here this element to w, and this element is sent to x. Well, so the uniqueness of the decomposition implies that you can define such a map. So once you have this notation, there is a result by Northgate. That tells you that you can relate the left preorder on W and the left preorder on Wi as follows. So let x, y be elements in W. Then, well, if x is less than left to y, then their wi components, namely their image under pi I, is less than left, and I put here the I in on the top because I mean that this relation is defined only in wi. But immediately you see from this result that in particular if x and y are already in wi, then they are related by the left preorder in w if and only if they are related by the left preorder in wi. So if x, y are in wi, x is less than left y is equivalent to x. So for stating the theorem, I need to precise here, but after the theorem is proved, we can assume that the relations are the same. I will not give a proof of this theorem, but I can say that the proof is very, very short and elegant. I mean, it's not 100 pages of computation. It's a very short paper by Meinhof. I don't know what it is, 2 or 3 pages of proof. That's completely. That's very beautiful proof. In particular, also, if x is equivalent left to y, then pi I of x is equivalent left to pi I of y. And again, I can put here an I or not. That's not a problem. Okay. Or it can be expressed also in a last form if C is the left cell of Wi. So assume that you are able to compute the decomposition. Assume that you want to work by induction, that you are able to compute the decomposition into left cells for all the parabolic subgroup, then this result tells you that if you multiply C by xi, well, this is not a left cell, that would be too easy, but this is a union of left cells. So in some sense, it gives you an upper bound for the left cell. If you work by induction, it gives you an upper bound for the left cells. Just a remark. I have said that the left relation, the left preorder relation in Wi and in W coincide when you restrict to elements of Wi. And this is also true for the right relation because you can take the inverse, that's easy. But this is false for the left-right preorder. So for instance, in this, in A3, with generators S, T, and U, and if you take I to be S and U, so the extreme elements, then in fact in W all the simple reflections are in the same two-sided cells. But S is not in the same two-sided cell inside Wi of U. It's not. Well. So this result, I have said, gives an upper bound for the left cell. I will give another result, which give some, which give a lower bound, and which is also pretty easy to prove due to Lusztig. So if X is in Xi, and if W prime are in Wi, and W is related to W prime by the left preorder in Wi or in W, that's the same thing again, then W times X inverse is less than left W prime times X inverse. The inverse of X is a distinguished coset representative, but on the right side. So if you multiply, if you do this multiplication, you will obtain all elements in W again by just taking the inverse. So this, in some sense, tells you that if you know some relations inside a small group, then you can obtain relations inside the big group. So in some sense, it gives you a lower bound for the left cells. Well, unfortunately, the lower bound and the upper bound don't coincide, for otherwise it would be too easy. And so the problem of computing the left cells is not solved only by these two theorems. Well, and I want to finish the list of, well, maybe a remark that I forgot. There is one left cell that we can compute all the time. This is the cell of the